Hello my dear friends, I am Shubham from LearnerHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnerhub.com. So then, let's start. So friends, in this video we are starting with your ICSE Class 9 Chemistry chapter number 4, Atomic Structure and Chemical Bonding. Okay, and we are going to learn in this video about the concepts of atomic structure. Okay, completely. And then we are going to move ahead to the chemical bonding part in the next video. But while learning the concepts, we will also go through some questions. We will solve some questions so that you would get a fair understanding that how much you have understood the concepts. Okay, so without wasting much time, let's start and let's rock. So let's quickly go through the topics which we are going to cover in this video. First of all, we are going to see the structure of atom, then atomic number, mass number, isotopes, then distribution of electrons in the orbits, then reason for the chemical activity of an atom, and lastly the octet rule. Okay, so first of all, when we are talking about the structure of an atom, let's start from the simplest thing, which is the atom. So what is an atom? We all know it is the smallest particle or smallest fundamental particle, we can say, of an element, okay, which shows all the properties of that element. Okay, smallest particle of an element which shows all the properties of an element. And we also know that this atom, okay, may or may not exist independently. For some elements it exists independently, for some elements it doesn't exist independently, right? So we know about oxygen and all those things. Oxygen molecule exists independently, not oxygen atoms, okay, and so on. And also, very important thing, in every chemical reaction these atoms take part. Okay, so this was all about atom, which is very basic. We know already till we have reached till the class 9th, we already know these things. Now moving ahead to this part, which is the structure of atom. Now here you have to start understanding the things, then you would get a hold of the concepts related to the structure of atom, okay, and concepts related to the bonding as well. So now our atom, okay, is made up of 3 subatomic fundamental particles, okay, subatomic or fundamental particles you can say. So these subatomic particles are electrons, protons and neutrons. Okay, now here we will see the symbol of these subatomic particles, okay, from which atom is made, and their charge. Okay, so electrons symbol is very simple, small e, protons is small p, neutrons symbol is small n. And the charge, okay, so we are not talking about the actual charge of electron, we are talking about the relative charge, okay, the charge relative to the proton. So charge of an electron, okay, relative to the proton is -1. Okay, so you can simply say that electron is having -1, okay, relative charge. Okay, relative to whom? Relative to proton, okay, or relative to neutron, okay, because see, neutron is having 0 charge, okay, so electrons are having -1 charge, okay, and protons are having +1 charge. Okay, clear? Now going ahead to the masses of this subatomic particles. So they have very less mass, okay, very low mass. So our electron is having, see, 9.1 into 10 raised to -28 grams. This is the mass of an electron. It's very less, right? You can try writing this number, okay, by putting the 0 and you would be like tired of writing those zeros. Okay, so I will suggest you to practically do this thing, then maybe you would realize that, oh, how small the number is and how small the mass of an electron is. Okay, now same case is with proton as well, but here you can see the number, the mass of the proton is 1.6 into 10 raised to -24. So it is more than electron, right? And the mass of neutron is also the same as that of the proton, okay, 1.6 into 10 raised to -24, 1.6 into 10 raised to -24. Okay, so this is all about the masses of our subatomic particles. Okay, now here I have told you that our atom, okay, is made up of these 3 subatomic particles, but there is an exception. Hydrogen atom lacks neutron. Okay, so hydrogen atom, this means only has electron and proton. Okay, fine. So we will see ahead how much electron and how much proton hydrogen atom has. Okay, for that only we have to study what is atomic number and all those things. Okay, but now moving ahead, first let's understand about the structure of atom entirely. So we have just now seen of which subatomic particles our atom is made. Now talking about the structure, you just simply think that, or you just simply understand that our atom is made up of two structural parts. Okay, one is the central part, okay, which is called as the nucleus. Okay, it's here in the center of the atom. Now this nucleus is positively charged. Why is this so? Because it is having protons and neutrons in it, because it is having simply protons in it. Okay, neutron doesn't have any charge, but why nucleus is positively charged? Because of this protons, because we have seen protons relative charge is +1. Okay, so which means protons relative charge is +1 means protons charge is positive. Okay, since protons are positively charged, therefore our nucleus is also positively charged. Clear? And yes, importantly, nucleus has both protons and neutrons inside it. Okay, so our protons and neutrons are present in the nucleus. Clear? Now the next structural part of the atom is the shells. Okay, or we can call it as an orbit. Okay, so we can also call it as an extranuclear part. Okay, extranuclear part means apart from the nucleus. What is there in the atom? We are having this shells or orbits. Okay, now what are these shells or orbits? Okay, I will just erase this. So these shells or orbits are the imaginary paths, okay, in which our electron revolves around the nucleus. Okay, so this, I have drawn a shell. So this is an imaginary path in which, suppose I am taking an electron. So this electron is revolving in this imaginary path, and this imaginary path is called as shell. Okay, so imaginary path in which electrons revolve around the nucleus. So not necessarily there should be only one shell, there can be 2, 3, 4, 5 shells. Okay, so we will see about it also. Which type of atoms have how many, means how atoms have different number of shells. Okay, that depends on which thing. Okay, all those things. Clear? So this was the basic part about the structure of atom. We should know that our atom is having two structural parts. One is the central part, which is nucleus. This is having protons and neutrons residing in it. And the another part is the extranuclear part, which are the imaginary paths in which the electrons revolve around the nucleus, which are called as shells. Okay, clear? Now, interesting thing about the subatomic particles, okay, which are electrons, protons and neutrons, is their mass. Okay, so I have focused or emphasized previously also on their masses, but you can try to relate, okay, slightly. See, electrons mass, okay, is less than the proton's mass. Correct? You can see 9.1 into 10 raised to minus 28 is less than 1.6 into 10 raised to minus 24. It's simple math. Okay, but you can also see neutron's mass is same as that of the proton's mass, right? So proton's mass is same as that of the neutron's mass, or neutron's mass is same as that of the proton's mass. Okay, I'm just writing in this way. So if I'm going to calculate the mass which is present in the nucleus, so what it would be? We know that our nucleus has protons and neutrons, right, in it. So the mass of the nucleus would be the sum of the masses of protons and neutrons. Okay, so see here, masses of proton, masses of neutron, they are exactly the same. If I would just add them, it would be like 3.2 into 10 raised to minus 24. Okay, so the mass of nucleus would be like 3.2 into 10 raised to minus 24 if I am talking about only one proton and one neutron. Okay, or suppose if I am talking about 10 protons, if suppose my atom is having 10 protons, 10 neutrons, and yes, obviously if there are 10 protons, there should be 10 electrons. Okay, we will see about it later. So here, this, if I would multiply this, okay, 1 proton's mass is this much, 10 protons mass would be 1.6 into 10 raised to minus 23. Okay, so what I will do is I will just erase this. I will write the masses so that you would get an idea. So what would be the mass of 10 protons? 1.6 into 10 raised to minus 23. 10 neutrons would be also the same, 1.6 into 10 raised to minus 23. What I'm doing is I'm simply solving this. Okay, 1.6 into 10 raised to minus 24 into 10. Okay, simple indices rule you can use, a raised to m into a raised to n. Okay, and then here 9.1 into 10 raised to minus 28 into 10 is 9.1 into 10 raised to minus 27. Now still, what would happen if I would add this to, it would be 3.2 into 10 raised to minus 23. And see here, the mass of 10 electrons is 9.1 into 10 raised to minus 27. So you can see clearly the mass of 10 electrons, and if I am seeing the mass of the neutrons and the protons which are present in the nucleus, or simply the mass of the nucleus. Okay, so I'm writing here mass of nucleus. This is the mass of electrons. Okay, just a minute. Electrons. I will just write it completely. So still you can compare and you can see this is 9.1 into 10 raised to minus 27. This is 3.2 into 10 raised to minus 23. Still the mass of the nucleus is like much more than the mass of the electrons. And what is the mass of an atom? It would be, right, sum of this mass of electrons and the mass of nucleus, because our atom simply has electrons, protons and neutrons, right? The nucleus and the shells. Our atom simply has the nucleus and the shells. In nucleus there are protons and neutrons. In the shells there are electrons. So the mass of an atom would be the sum of mass of electrons, protons and neutrons. But you can see here mass of electrons is very less. So we can say that, okay, the mass of the atom, okay, entire atom, suppose these are the shells, okay, and this is the nucleus. So mass of the entire atom, okay, so most of the mass is here in the nucleus, okay, because mass of nucleus when compared to the mass of electron, it is much more, okay, than the mass of electrons. If I would add both of them, then what I would get? I would get the mass of an atom, right? But in that mass of an atom, the majority portion would be of mass of nucleus, right? This part is the majority portion, because this is a greater number, this is a smaller number, right? So majority portion would be of this, that is the mass of nucleus. So we can say that our atoms, most of the mass is because of the mass of the nucleus, and electrons have very less mass. Clear? So this was the relative terms which I wanted to explain to you in terms of masses, okay, when we are considering an atom. Okay, understood this part? Okay, so I hope now now the structure of atom is pretty clear to you. Now let's move ahead to the atomic number. Now these things would add up to the concepts of the structure of atom, okay, because your conceptual clarity will become more and more, means concepts would be clear to you more and more when we study these things, atomic number, mass number and all those things. Okay, so starting with atomic number. Now what is this atomic number? It is simply the number of protons in the atom or number of electrons in a neutral atom. Okay, so here the term neutral, okay, you would say, sir, why is the need of this neutral term? Now let me tell you, see, R number of protons and number of electrons, okay, in an atom, in a neutral atom, okay, I'm talking about a neutral atom, are same. Okay, so if I'm talking about a neutral atom, I have told you number of protons and number of electrons are same. This means that our atom is electrically neutral. Okay, so in short, simply see, whenever we are having an atom and if it is not having any charge on it, okay, we can clearly say that the number of protons and the number of electrons are same in that atom. Okay, because our atom likes to maintain the electrical neutrality. Okay, our atom doesn't want the positive charge to exceed than the negative charge. It wants very much same behavior, okay, of the positive, which it wants very much same amount of positive charge and same amount of negative charge in it. Okay, so this means that if I'm telling that number of protons in an atom is atomic number, so we also know that in an atom, okay, if there is no charge on the atom, okay, so if we are talking about a neutral atom, then the number of electrons would also be equal to the number of protons, right? So that's why our atomic number is also the number of electrons in a neutral atom. Okay, clear? Now let's take an example. Suppose for carbon, okay, now we know we have learned the first 20 elements in our periodic table. Okay, so atomic number of those first 20 elements are also exactly the same. When you are talking about the first element as hydrogen, its atomic number is 1. When you are talking about helium as the second element out of the first 20 elements, its atomic number is 2. Okay, so the sequence in which you have studied in the sequence or the sequence in which you have remembered the names of the first 20 elements is exactly the same sequence for the elements having atomic number, okay, from 1 to 20. Okay, clear with this point? So this means that if I'm writing down the atomic numbers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then again 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I have to just write exactly the same sequence of first 20 elements which we have studied. Okay, so which is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and then again sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and then calcium. Okay, so I have just written the symbols. Now we can see that carbon's, okay, atomic number is 6. This means that our carbon, okay, the neutral atom of carbon, okay, is having 6 electrons and 6 protons. Okay, now you can tell me what would be the number of electrons and the number of protons in the potassium. Okay, I won't tell you because the answer is on the screen itself. You can pause it here, you can use your brains, and then you can get to the answer. Okay, okay, fine. Moving ahead, so this means that we have seen here, okay, every element's atom is having a unique atomic number. Correct? Hydrogen's atom would have always 1 as the atomic number. Helium's atom would have always 2 as its atomic number. Okay, so you have to remember this thing, that unique for atom of each element is its atomic number. Clear? And this thing I have already explained to you. So this was all about the atomic number. Let's move ahead to the mass number and then try to correlate the mass number with the atomic number as well. Okay, so it would be pretty interesting. Okay, just pay attention. So what is mass number actually? Mass number is sum of, see, you can see here, plus sum of number of protons and number of neutrons present in the nucleus. Okay, so now I don't think it's necessary to write the nucleus because we already know that protons and the neutrons are present in the nucleus, right? So mass number is simply the number of protons plus number of neutrons. You just add both these numbers, you would get the mass number of that atom. Okay, but interesting part is, okay, now I'm just writing CA. Okay, the atomic number symbol is Z. Okay, you have to just remember this thing. If I have missed this thing, okay, sorry. So you just remember atomic number symbol is Z. Okay, so what I can write is Z is equals to, we know it is equal to the number of protons or it is equal to number of electrons in the neutral atom. So I'm just writing number of protons or Z equals to number of electrons, okay, in a neutral atom. Okay, clear? Now in case of mass number, I have told you mass number is simply the number of protons plus number of neutrons. Okay, so I can just write it here itself. Okay, just erase this nucleus and I will just simply write here is equals to E. Okay, now if you don't want to, means we can simplify this thing. Okay, so instead of writing number of this term, I can just simply write Z is equals to P. Okay, you just understand this thing that P means number of protons, and I can also simply write it is also equals to E because we already know Z is equals to P, which means number of protons in the atom, and we also know atomic number is also equal to the number of electrons present in the neutral atom. So we can write this Z is equals to P, which is equals to E, right? And we already know P is also equals to E, right? Number of protons is equals to number of electrons. Same way, I can write A is equals to N plus P or P plus N. Anything would be, means you can write in either way. That's not an issue. But now we have to relate the mass number with the atomic number. And there is a wonderful thing which we can derive from this. We can find out number of neutrons by looking at the mass number and the atomic number. Okay, how? See, number of protons is actually atomic number, correct? Just now we have studied. So instead of P, I can write here capital Z. Okay, fine. So then I can again rewrite this equation as A is equals to N plus Z. Okay. Now, if I want to find number of neutrons, see, if I'm having mass number, if I'm having atomic number, I can find number of neutrons. How? Simply rearrange this equation as this. Like, see, n is equals to a minus z. So number of neutrons is equals to a minus z. Okay, understood? Okay, so now this entire thing, the concept of atomic number and mass number, we are like going to collaborate it. Okay, and we are going to use these two concepts of atomic number and mass number to write the symbolic representation of an element. Okay, so how we have to write the symbolic representation of an element? See, suppose our X is an symbol of an element. Okay, here now you would tell me what would be A. Okay, just now we have studied A is the symbol for mass number. Okay, I can hear you. Okay, you should be guessing the answers. Okay, or you should be trying to give the answers. Okay, there is simply no point sitting on a sofa and watching this video lecture as a couch potato, because this is science. Okay, friends, you need to use your brain, you need to apply the concepts. Okay, you need to try to correlate the concepts as well. Okay, so see, so this is A means mass number, right? Just now we have seen, and Z is atomic number. So we can symbolically represent an element by these two things, mass number and atomic number, along with the element, along with the symbol of the element as well. Okay, so for example, I am taking chlorine. Okay, so chlorine's atomic number is, chlorine's mass number is 35 and chlorine's atomic number is 17. So see, what I have done is, X is the symbol of an element, A to Z, you can remember in this way, A to Z. Okay, our alphabets start from A to Z, right? So A to Z, right? And A is mass number of the chlorine, Z is atomic number of the chlorine. Okay, and X is the symbol of chlorine. Okay, so in this way I can represent chlorine. Clear? So this is the symbolic representation of an element. Okay, now here we are going to start studying an interesting topic or interesting concept, okay, which is related again to the atomic number and the mass number. Okay, so that's why I have included it right away after we have studied this, okay, which is isotopes. Now in this word itself, I'm going to give you the hint how to remember what actually are isotopes. Okay, so first of all, let's see what are isotopes. So isotopes are the atoms of same element. Okay, you have to remember atoms of same element. Clear? But these atoms, okay, they are having same atomic number but different mass number. Okay, so how you can remember this? See, in the word isotope, you can see here there is a P and there is a E. Also there is a word iso here. Okay, so iso means same, and we know P and E, so we can just correlate. P means protons, E means electrons, and number of protons and number of electrons, we can just think in this way. So this is something about number of protons, number of electrons. So number of protons and number of electrons are same, correct? So same number of protons and number of electrons. So if number of protons and number of electrons, okay, means number of protons or number of electrons, okay, either of these two things is same in case of the atoms, what would happen? Their atomic number would be same, right? Because atomic number is simply number of protons, or it is equal to number of electrons in the neutral atom. So if either number of protons or number of electrons is same in case of two atoms, right? So ultimately it means that the atomic number is also same. Clear? So here let's see some examples so that it would be clear to you. So starting from the example of hydrogen. So hydrogen is having 3 isotopes. Okay, so how now we are going to represent it? Just a few minutes ago we have studied the symbolic representation. In that manner I am going to represent, and then we will start to correlate, okay, the definition of isotopes or what are actually isotopes with that symbolic representation. Okay, so I'm just writing here, see, 1H1, okay, 2H1 and then 3H1. So now we know A to Z in center there is the symbol of element. So this means that this is A. A means mass number. So we are talking about here about the mass number. So everything written on the top means numbers written on the top are mass numbers, correct? And A to Z, right? A to Z. So numbers which are written at the bottom are the atomic numbers. So now you can just correlate with the isotope. Means what is actually isotope? The atoms of same element. These all are the atoms of hydrogen, but they are having same atomic number. See, same atomic number, atoms of same element having same atomic number, Z is atomic number, but different mass numbers, Okay, got the point? Clear? Chalo. Moving ahead, let's see the isotopes of carbon. 12C6, 13C6 and 14C6. These are the three isotopes of carbon. Okay, this is comma simply. Fine. So here also see atomic number is same. Okay, again A to Z. Okay, atomic number is same but mass number is different. And again one more example we have to study in our syllabus is chlorine's example. 35 chlorine 17 and 37 chlorine 17. So you need to remember these things. Okay, so these, see, again same atomic number but different mass numbers. Okay, so this is all about the isotopes. Okay, so now so far we have learned whatever the concepts. Okay, let's check whether how much we have understood. Okay, so I am having a very simple question. Okay, but you have to apply your brains to solve this. So the question is, see, I have given a table here. Simply there are names of some elements. Okay, some names are missing. There are symbolic representations, some of them is missing, and there are number of protons, number of neutrons and number of electrons, out of which some of here the number of neutrons are missing. Okay, rest all is completed data. So by using this data, okay, you have to just focus on one row at a time. Okay, see the name of an element, see the symbolic representation, see the number of protons, number of neutrons or number of electrons, whatever is given, and try to find out whatever they are asking you, which is given by simply a question mark. Okay, so I'm giving you a quick 1 second, so you can just take a screenshot or whatever you want, and then, or you can pause it here and you can try to solve it on your own. Okay, suppose now I am assuming that you have solved it on your own. Means I hope you would have definitely tried to solve it on your own, and I hope you would have got the answers as well. Okay, but let's try to see what are the answers. Okay, you can check on your own answers as well. Okay, so now I'm telling the answers. If some of you may not have got the answers, no worries, we can learn how to reach to the answers. You can again try to understand the concepts, okay, in a better manner. Okay, if you feel you have not still understood, you can just go back again, understand the concept, and again come back and try to solve the questions. Okay, so let's see what would be the answer for this question mark here. So symbolic representation for sodium is given as 23Na11. Okay, so what they have given is actually the atomic mass number A and the atomic number Z. Okay, now they have given us number of protons, they are asking us number of neutrons, and they have given us number of electrons as well. Okay, so we know number of protons and number of electrons, okay, in an atom, okay, they are absolutely the same. If you are talking about a neutral atom, so yes, we are here talking about neutral atom only, so absolutely the same. Okay, no charge on the atom. And here, so this two numbers is equal to the atomic number of proton or number of electron in the neutral atom. It's equal to atomic number, and you can see correlated. Atomic number is also 11, so it's right. Okay, now they are asking us number of neutrons. So just now, a few minutes ago, we have studied the formula to calculate the number of neutrons, provided if we know what is the mass number and the atomic number. So number of neutrons was equals to A minus Z, right? So mass number minus atomic number. Okay, so we have derived this. So A is here 23, Z is 11. 23 minus 11 would be simply 9, and here 3, it's 12. So here the number of neutrons is 12. Okay, very easy. In the same manner, see, uranium is given. They are asking us the symbolic representation, number of protons, number of neutrons, number of electrons is given. So we need to just write the symbolic representation. So symbolic representation is X, A to Z. Okay, so uranium's symbol is U. I am telling you this thing. Okay, if you don't know, you can just Google it and you can just get the answer. Okay, because I am not expecting from you that you should know the symbol of uranium right away from this means part, but if you know, it's better, it's well and good. Okay, because if someone asks you, you already know that thing, right? Chalo. And it is also a very known element as well. You would hear about uranium here and there. Okay, so see, uranium symbol is U, X is done. Now remaining part is A and Z. So A is mass number is actually the sum of number of neutrons and protons. Okay, so here number of protons, number of neutrons they have given us, we need to just add them, we would get mass number. So see, 146 and 92. So if I would add them, so it's 246 and then I would subtract 8 from it. So 6, 8, so 238. Okay, 238 would be the mass number. You can do either way, you can just add it. Okay, I did it my way. Okay, simply adding also would give us 238. And Z is the atomic number. Okay, which is equal to number of protons or number of electrons. Okay, number of electrons in neutral atom. So see, number of electrons 92, number of protons 92. Okay, so since the number of electrons and number of protons are same, this means that we are talking about neutral atom only. Okay, how you can just figure out the atom is neutral or not? You can just see the number of protons and number of electrons. If they are exactly the same, this means the atom is neutral. Okay, so in a neutral atom, atomic number is equal to number of protons or it is equal to number of electrons in the neutral atom. Okay, so 92, 92. So atomic number is simply 92. Okay, number of protons or number of electrons in neutral atom. So 92. So here I'm just going to write 92. Okay, fine. Now here they have given us symbolic representation in third row, number of protons, number of neutrons, number of electrons. They are simply asking us the element's name. Now for this, no need to see actually no need to see about atomic mass and atomic number and all those things. You can just simply see the symbol and you can guess the name of element. That's pretty simple. So F is the symbol for fluorine. So simply our answer would be fluorine, right? Fine. So if in case you are not able to remember the symbol by looking at the symbol, if in case, because it should not be the case, because you should thoroughly know the names and the symbols of the elements of first 20 elements. Also you should know now the names and the symbols of the elements having atomic number from 1 to 20, which is exactly the same, okay, as that of the names and the elements of first 20 elements. So here you can see the atomic number as well, it's 9. So atomic number 9 is fluorine. So you can also get back to the answer in this way as well. Okay, now another method. Clear? Okay, tan-ta-dan. So now we are moving ahead to the next topic, next concept, which is how we are going to distribute the electrons in the orbits. Okay, so distribution of electrons in the orbits. How actually the electrons are distributed in the orbits. So this distribution of electrons in the different orbits is actually called as electronic configuration. So suppose if someone is asking you about what is electronic configuration, you can simply say that distribution of electrons in the different orbits. That's simply the electronic configuration. Okay, now this distribution, how to do the distribution, was suggested by Bohr and Bury, and they gave some rules which we need to follow. After following those rules, we can correctly distribute the electrons in the orbits. Okay, or we can show the correct distribution of electrons in the orbits of that particular atom. Okay, so we can tell, okay, others that, oh, in this atom of this element, the electrons are distributed in the orbits in this manner, if we know these rules. So now what are these rules? Very simple rules are there. First rule is the 2n square rule. You can just remember in this way. 2n square rule means here, okay, n here in this 2n square, this n is actually the number of shell which we are considering. Okay, so if I am considering first shell, okay, then I would put 1, okay, I would substitute n as 1 and 1 square I would write because it's n square, and then I would calculate. So 1 square is 1, 1 into 2 is 2. So whatever answer I would get, that would be the maximum number of electrons which can occupy that shell. Okay, so here we were talking about first shell. Okay, so I'm just going to represent it in this way, so it would be easier for you to remember or just visualize. So this is nucleus n, this is the first shell we are talking about. Okay, now here I have calculated by using this 2n square rule what would be the maximum number of electrons which can be distributed to this first shell, or which can accommodate this first shell. Okay, so maximum number of electron is, I have just I have just substituted n as 1, I have calculated it, it is 2. So whatever answer I would get, that is the maximum number of electrons which can accommodate that shell. Okay, so 2 electrons can accommodate, maximum 2 electrons can accommodate first shell. So I'm just writing here, see, in this way, 1, 2. Fine, let's move ahead. If I'm talking about second shell now, okay, chalo. So I would make a second shell. Now again, you know the simple trick, we have to just put 2 or substitute 2 in the place of n. So here it's second shell. So 2 into, it would be 2 square, right? N as 2. So 2 square is 4. 4 2s are 8. So the maximum number of electrons which can accommodate second shell is 8. Okay, so in this second shell, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now moving ahead, third shell, in the same manner now. Okay, third shell, 2 into 3 square. Okay, 3 square is 9, 9 2s are 18. 18 electrons can, maximum 18 electrons can accommodate in the third shell. Okay, so this I'm drawing third shell. Now you can just, now it's pretty much understood that, you know, I'm going to write E 18 times. No, I'm not going to write E 18 times. Okay, you can write if you want to, but the main thing which I wanted to explain you is this: how we can know that in which shell how much maximum number of electrons we can accommodate, okay, or we can distribute to it. Okay, so fourth shell would be as usual, it would be the same. Fourth, same logic, 2 into n square means 4 square, so 16 2s are 32 electrons can accommodate in the fourth one. Fifth one also would simultaneously go, means fifth one also would be the same manner. Okay, so I hope you would have understood this first very much important rule, which is 2n square rule. Okay, but the story doesn't end up here. You need to club 2 more rules with this rule, and then you can correctly tell that in that particular atom of an element how the electrons are distributed in different shells. Okay, so I hope you know that Bohr's model of an atom. Okay, he told that the shells, he named the shell as K, L, M, N, like this. Okay, first shell is K, second is L, third is M. So you can just simply write this way also: K shell, L shell, M shell, N shell, in this way. Okay, so electronic configuration, you can, I will tell you how to write it, but we can use this KLMN, okay, in this manner, okay, from the Bohr's model. Clear? Let's move ahead to the next 2 rules. Very simple rules. The second rule is very simple. Shells are filled in the stepwise manner. Absolutely, we would fill the shell, okay, first shell, then second, then third, then fourth. Okay, we won't abruptly fill the first shell, then skip 2 shells in between, second and third, and then directly fill the fourth shell. No, this won't happen. Okay, they would be filled in the stepwise manner. Clear? Then outermost shell of an atom, very important rule. You need to, means you can mark it as a star. You need to remember this thing. Until and unless you follow this thing, you would not write the correct electronic configuration of the particular atom of an element. Okay, so what is the rule? Outermost shell of an atom, okay, outermost shell of an atom cannot have more than 8 electrons. Put it in your brains, okay, very clearly. Okay, fine. So here there are some exceptions, which is hydrogen and helium. Now why is this so? You think it logically, na? These 2 elements have atomic number, okay, respectively as 1 and 2. This means that they have simply the number of electrons in their neutral atom as 1 and 2. So if they are having only 1 and 2 electrons, how their outermost shell would have more than 8 electrons? There is no possibility, right? So their outermost shell can have maximum 2 electrons. Because why? See, they are having since 1 and 2 electrons, okay, and first shell only has the capacity to accommodate 2 electrons, okay, and these atoms don't move beyond 2 electrons. Hydrogen, okay, it is having 1 electron, but it craves for 1 more electron, okay, and it gets that 1 more, and after it gets that one electron, means 1 extra electron, it has now total 2 electrons. So those 2 electrons are accommodated in the first shell itself, and its first shell is the outermost shell. So here you cannot apply that its outermost shell, okay, cannot have more than 8 electrons. Okay, so here there is no chance of having more than 8 electrons. It's a simple logic. Okay, fine. Now, so let's take an example. So suppose if I'm talking about, okay, calcium. Fine. Okay, I will make you understand this thing. So calcium's atomic number is, okay, is you can tell me. Okay, fine. I hope you would have answered this. So it is 20. Fine. So I'm writing is here Z is equals to 20. Okay. Now I need to distribute these electrons by keeping in mind these 3 rules. Okay. So first of all, I will fill the first shell, right? So first shell is the K shell. Okay. So in K shell, first shell, I can accommodate maximum 2 electrons. So out of this 20, if I'm distributing 2 electrons in them, in the first shell, how much would be remaining now? 18 would be remaining now. Okay, I'm just writing here 18. Now these 2 have accommodated in the K shell, okay, or the first shell. Then remaining 18 I need to accommodate in the next shells. So next shell is the L shell. Now I know the L shell's maximum capacity is 8. You need to remember this thing. Okay, how you would remember 2, 8, 18, 32 in this manner. 2, 8, 18, 32. We have already done this, right? We have already calculated this. 2, 8, 18, 32. Fine. So second one is 8. So out of this 18, if I would distribute 8 electrons here, no issue. Fine. Okay, so now out of this 18, I have distributed 8 electrons in L. I have accommodated 8 electrons in L shell. So now here would be now 10 electrons remaining. Okay, out of 18, 8 has gone now. So 10 is remaining. Fine, chalo. Let's move ahead to the third shell now. Okay, so K, L, then M. Now M's capacity is 18 electrons, right? Now I'm having 10 electrons. So I can simply put this 10 electrons in the M shell and my electronic configuration is over. If you are thinking in this way, you are going wrong because you are missing this third rule. Okay, which is the outermost shell must not have more than 8 electrons. And since if we put this 10 electrons in this M shell, this would become the outermost shell, but it would have more than 8 electrons, which is not allowed, So what we have to do is, now by hook or by crook, we don't have any choice. So we cannot fill 10 electrons in this, okay, because we cannot make our outermost shell having more than 8 electrons. So what we need to do is, we need to then give 8 electrons to the M. Okay, so 8 is the number which you can think that, okay, it is a stable number. Okay, stable number of electrons. So that's why if we are having more than 8 electrons, and if our last shell, though it has the capacity to accommodate more than 8 electrons, but still we cannot give that last shell more than 8 electrons because our rule says that. Okay, we should not give. But then what to do in this case? You can give 8 electrons to this shell and the remaining electrons you can push forward to the next shell. Okay, so out of this 10, I would give 8 electrons to the M and the remaining 2 I would push into the next shell. Okay, so here in the M shell I would give 8 electrons. Okay, fine. Okay, so now what is remaining? 2 electrons are remaining, K, L, M, and then it's N. So I would just give 2 electrons to the N. Okay, so this would be the electronic configuration, okay, for the calcium atom in terms of the shells. Okay, fine. 2, 8, 8, 2. So now further moving ahead, no need to write always this K, L, M, N. If you want to tell the electronic configuration to anyone, okay, you can simply just write in this way: 2, 8, 8, 2. You just simply write the number of electrons in that particular shell. No need to write K, L, M, N every time. It's understood. You are moving ahead from K to L to M to N, or from first shell to second to third to fourth. Clear? So if someone asks you write the electronic configuration of calcium, you can simply write this: 2, 8, 8, 2. Fine. So I hope I have explained you all the 3 rules, how to use those rules to write, and also how to use those rules to correctly write the electronic configuration of an atom, of an element. Okay. Now just now we have seen how to distribute the electrons in the different orbits. So let's quickly go through some questions. Okay, let's see how much you have understood, how you can use your brains to write the electronic configuration of, first is potassium and then is aluminium. So you can pause it here, you can try it on your own, and then you can resume back to see the correct answers. Okay, so I hope you would have tried. Chalo, let's start with the answer. So potassium's electronic configuration, first of all we need to find out the atomic number. So this thing would be this thing. You can get this thing. How? Because you already remember the atomic numbers, you already remember the names of the elements having atomic number from 1 to 20, and you know potassium comes in that names, right? And potassium is the 19th element, right? Atomic number then simply is 19, correct? So Z is equals to 19. Now I need to distribute 19 electrons in the shells. So what I can do is, initially what you do, you just write this KLMN, okay? You can write the capacity as well, because it's very much new to you, okay? I know all these things, right? But it's new to you. So thinking from that point of view, from that perspective, I will tell you a simple trick. You just write KLMN with pencil, then you just write the capacity of that shells as well, okay, with the pencil itself. So 2, 8, 18, 32. So that ways in your brain you would be always clear that, oh, I don't need to give more than the capacity of that particular shell, more electrons than the capacity of that particular shell, okay? So now here again, starting from the 19 electrons, so first I will accommodate 2 here simply, then 8 here, so total would be 10, right? So 10 electrons I have accommodated, remaining there are 9 electrons. Again the same problem. If I would give 9 electrons to this M shell, this would be the outermost shell, but it would have more than 8 electrons, which I cannot tolerate at all, right? Because it's the rule. So I need to do what? Again, split, giving 8 electrons to M and remaining electrons to the next shell. So out of 9, remaining 9, I would give 8 to M, 1 to N. So 8 to M, 1 to N, and this would be our electronic configuration. So after that, what you can do is simply, you can, after writing this, you can just simply erase this. That's it. And you can just simply put the commas and the columns, brackets, okay, fine. Aluminium. So aluminium would be pretty easy. Aluminium's atomic number is 13. Okay, now accommodating 13 electrons, again KLMN, okay, 2, 8, 18, 32. Then again, out of this 13 electrons, 2 and 8 electrons would be simply occupied here, okay. Then remaining are 3 electrons. Now 10 electrons are occupied, remaining are 3 electrons, and we can give 3 electrons to M, and yes, our outermost shell, see, it is having less than 8 electrons. So after writing the electronic configuration, every time you need to check this thing once, that our outermost shell, is it having less than 8 electrons? If it is not having, split it, give 8 electrons to that shell, and next remaining number of electrons to the next shell. Okay, so here it is already number of electrons are less than 8 in our outermost shell, so we have just distributed it in the correct manner, keeping in mind the capacity of the particular shell. See, I am just giving 2 electrons here, not more than 2, because its capacity is 2. I will not give more than 8 to L because its capacity is 8. It cannot take more than 8. Okay. But yes, here the M's capacity is 18, but still I need to think once that I cannot give more than 8 to the last shell. Okay, so here that's not the problem. Here 2, 8, total is 10 electrons, remaining are 3 electrons, which I can simply give to M, and also its capacity is more than 3, obviously its capacity is 18. Also, being the last shell, it has electrons, number of electrons less than 8. So yes, less than 8, right? So everything is satisfied. Simply then we will just erase this comma, and this would be our electronic configuration for aluminium. Okay, this is for potassium. Okay friends, so now moving ahead to the second last and very much interesting concept of this topic, which is the reason for the chemical activity of an atom. Okay, so what does this mean? Chemical activity means, see, our atom is not like a saint that it would just do meditation very quietly. Okay, atom's nature, okay, doesn't fit into that picture. Our atom is like something who is running here and there and trying to interact with the people and all those things, but not all atoms do those things. Okay, there are few atoms which really sit quietly, meditate like the saints. Okay, but now see, what is the factor which is making some atoms run here and there, interact with people, travel and all those things, and do masti and all those things, and what is making some atoms to sit quietly and meditate? Okay, that's the simple logic we need to understand, and this is what actually is chemical activity of an atom. Okay, So why particular atoms are chemically active, which means why particular atoms react with other atoms, and why particular atoms are not chemically active, which means why particular atoms do not chemically react with the other atoms or do not interact with the other atoms. Okay, so this chemical activity of an atom depends upon a very important thing, which is the number of electrons in the outermost shell. Okay, now outermost shell is called as valence shell. Okay, you just need to remember this thing. Fine. So in that particular atom, okay, how many number of electrons are there in its outermost shell, that decides our atom would react with other atoms, okay, travel and explore and all those things, or it would not react with other atoms and meditate like the saints. Okay, fine. So it depends on the number of electrons in the valence shell. Now, if you need to remember this thing, our atom is having 8 electrons in its outermost shell. Okay, which means that complete octet of valence shell, outermost shell, valence shell. Fine, the same thing. Octet means 8 electrons. So in simple words, if our atom is having 8 electrons, okay, sorry, 8, just simply E. Okay, so 8 electrons, okay, in the outermost shell. So we say that our atom is having complete octet of its valence shell. Octet, 8 electrons of valence shell, outermost shell. So 8 electrons in the outermost shell or complete octet of valence shell. Okay, then our atom behaves like the saints. It starts to meditate, which means that it is chemically inactive. It doesn't interact with other atoms. Okay, and when we say it is chemically inactive means, see, it's a simple logic of the nature. Every damn single thing in this world wants stability. Okay, every single thing. So our atoms also want the stability. Okay, fine. But now see, which atoms are stable? You need to remember from this point that those atoms having 8 electrons in their outermost shell, they are inactive. Okay, they'll tend to be quiet and tend to be very much saint-like behavior, having saint-like behavior. So this means that they are very stable, because you only think a person who is meditating, who is very calm, who is very silent, okay, or who is a very calm person. Okay, suppose there is a calm person and there is a violent person. So who is more stable? Okay, who can do things more actually efficiently? Okay, the violent person would end up doing mess, but the calm person would always think of doing the things in an efficient manner, in a correct manner, in a right manner, right? So a calm person, you can say that it is more stable. So here also the calm atoms, we can say that they are stable. Fine. So which are such type of atoms, or which are the elements, okay, which are the atoms of such elements? Okay, so the inert gases, we also call them as noble gas elements. Okay, so these elements, okay, are having complete octet of the valence shell, or we can say they are having 8 electrons in their outermost shell, and that's the reason they do not interact with their own atoms as well as with the atoms of other elements. Okay, so the elements of these atoms, okay, since they are having, or I can say the atoms of these elements, inert gas elements, okay, for example, now just leave helium for now. Okay, I'm just talking about neon, argon, krypton, xenon and radon. Okay, so these 5 elements, the atoms of these 5 elements, okay, are having 8 electrons in their outermost shell. That's the reason they do not interact with the atoms of their own elements, okay, or the atoms of other elements. Okay, so they are chemically, so we can say they are chemically inactive because they don't interact, and in turn we can say that they are stable. Okay, now why I have accepted this helium? Helium is also an inert gas element, and also it is also a very chemically inactive, or means it is also a stable element. Okay, but it doesn't have this complete octet of valence shell. Why? Again the same reason, because helium is maximum it can have 2 electrons and it is only having one shell, so its only shell, okay, Okay, helium is like this. Helium is like this, nucleus and one shell, okay, in which it is having maximum 2 electrons. Okay, that's it, fine, because its atomic number is 2. So the 2 electrons need to be distributed. They are distributed in the first shell, so it will only have one shell. That shell is only its outermost shell, and it is completely filled as well. That's why, since its outermost shell is completely filled, okay, that's why it doesn't feel the need to interact with the other elements, or interact with the atoms of, interact with simply with the atoms of other elements, or its own type, or its own helium atoms as well, okay, other helium atoms as well. Okay, so here the logic behind the inactivity is the complete octet of the valence shell. Clear with this point? Okay, and in case of helium, it is the completely filled first shell of the helium, okay, which is having 2 electrons. Clear? Now the thing would be reversed for chemical activity of the atom, okay, or chemically active atoms. They will not have complete octet of valence shell. Okay, so I can write incomplete octet of valence shell, which means less than 8 electrons, less than 8 electrons, sorry, 8 electrons in outermost shell, okay, or valence shell. Fine. So if the atoms of particular elements are having less than 8 electrons in their outermost shell, this means that they are chemically active. Since they are chemically active, they react, they interact with other atoms, okay, so this means that they are not stable. Fine. So I can say that they are unstable, okay, they are reactive. Fine. So understood the concept of chemical activity of atom. Okay, fine. Okay, so far you know that 8 electrons in the outermost shell is playing a very crucial role in the stability of the atom, right? And as I have told you, every damn single thing in this world needs the stability. So our atoms also need the stability. So looking into these things, okay, what our Cosell and Lewis gave is, they gave simply a electronic theory of chemical bonding. Okay, now slowly and gradually we are going to transit from the atomic structure to chemical bonding now. Okay, so this is the point of transition in the chapter, which is Octet Rule. So now our atoms need stability, and Cosell and Lewis gave this theory of chemical bonding, which is also called as simply the Octet Rule. Okay, now what is this Octet Rule? What Cosell and Lewis tried to tell us? Okay, they told that, see, atoms, okay, they tried to explain us how atoms combine. Fine. Okay, so now see, we know that there are some atoms which don't combine, which don't interact. Those are the atoms of inert gases. But there are some atoms, okay, but most of the atoms, most of the elements atoms, yes, they combine because their outermost shells do not have 8 electrons. Okay, only this 6 atoms, only these 6 elements atoms have 8 electrons in the valence shell. Okay, so they are only chemically inactive. Rest all the elements, they don't have 8 electrons in the valence shell, so they are like chemically active. Okay, and now talking about the chemically active atoms, Cosell and Lewis told that these atoms are chemically active, so they combine, okay, with the atoms of other elements or with the atoms of their own elements. Okay, but how they can combine, that thing they told us. So how they can combine? They can combine by either by transfer of valence electrons. Okay, now valence electrons are, see, I have told you, valence shell is the outermost shell. So valence electrons would be the electrons, number of electrons in the outermost shell. Okay, number of electrons in the outermost shell. Fine. So how Cosell and Lewis told that atoms would combine? First, either by transfer of valence electrons or the transfer of electrons in the which are present in the outermost shell, okay, from one atom to another atom. Okay, so this transfer can be like one atom is giving some electron to another atom and the another atom is taking up that electron from that particular atom. Okay, so here what is being done? Here there is a losing of electron and gaining of electron. Okay, so this transfer process always involves losing and gaining of electrons. Fine. While the another way, either way or the another way, Kosel and Lewis told they can follow, the atoms can follow for combining, okay, with each other is by sharing of their valence electrons. Okay, so they won't transfer. One atom won't completely give its electrons to another atom, and another atom won't completely take up those electrons. Okay, what they would do is they would see that, see, you also need electrons, I also need electrons. What we can do is we can share. Simply the way you and your best friend does with the one single chocolate. Okay, you think that your best friend should also be happy, your best friend thinks that you should also be happy, so you just share that chocolate. So in the same way, these atoms, okay, they are quite mature, you can see. Instead of these atoms which transfer the electrons, these atoms are quite mature. Okay, I'm just joking. Fine. So they share the valence electrons. So these are the two ways in which atoms can combine. Okay, Kosel and Lewis told, and why, and they do these things, this transfer of valence electrons or sharing of valence electrons, in order to attain the octet in their valence shell. In order to attain simply 8 electrons in their valence shell, in their outermost shell, in order to attain or in order to have those 8 electrons in their outermost shell. Fine. For this reason, they do these things, which means that, see, we know having 8 electrons in outermost shell is like super crazy thing for the atoms. Okay, because doing this thing, they become stable, right? So they are like super crazy about having the 8 electrons in their outermost shell. Okay, so in short, Kosel and Lewis told that atoms combine in this manner just simply to become stable. Fine. Okay, how they become stable? By attaining 8 electrons in the valence shell, because attaining these 8 electrons in their valence shell makes them stable. Clear with this point? Now, how this transfer of valence electrons from one atom to another atom, or how the sharing of valence electrons between the atoms takes place, this thing we are exactly going to study in the next part of the topic, which is ionic bonding and covalent bonding. So students, we have reached the end of this video, and I hope you would have enjoyed learning with me. You would have understood the concepts which we have learned so far. Okay, but please do let me know this thing in the comment section. I would be waiting for your comments, right? And as you all know, learn of matlab free hai par best hai. So see you in the next video with the next concepts of this chapter. Till then, keep studying. Bye bye and have a great day.